Okay, so this is chapter 17, and here we're going to be talking about energy and how to solve problems using kinetic energy, work, the principle of work and energy, and also the conservation of energy principle. So let's start by writing the kinetic energy. So if we have a solid, right, that is moving, two things may happen, right? So let's say this is the center of mass G, and then two things may happen. It may be translating, right? So it has a velocity Vg, and it also may be rotating about the center of mass. So the way we're going to do this is we're going to write the kinetic energy of the body as the kinetic energy of translation, which is 1/2 the mass of the body here. So this is the total mass of the body times the velocity of the center of mass square plus the energy of rotation. So this is translation and this is rotation. So we write those two terms, and that's all we need to write the kinetic energy. So 1/2 mv squared plus 1/2 I omega squared. Energy, kinetic energy of translation and kinetic energy of rotation. Notice that this is about the center of mass. So now there are two simplifications that you can do if there's no rotation. If there's just a pure translation, then this term is no longer there, and all you are left with is the translation part. Another simplification is when you have a pure rotation. Let's say you have a body that is attached somehow here and it's rotating about that point. So we start from our equation, right? So this is the kinetic energy, which is the kinetic energy of translation plus rotation, right? So now, because this is rotating about that point, we can write that the velocity of the center of mass is equal to the position of the center of mass times omega. So we can take that equation and put it here and simplify this. So you're going to get that this is 1/2 Ig, which came from here, right? Plus m Rg squared and then an omega squared here. And if you remember the parallel axis theorem for the moment of inertia, this is just the moment of inertia about O. So all this reduces to a rotation about O. So the kinetic energy is just 1/2 the moment of inertia about O times omega squared. Those are the two simplifications that occurs. So if there is just a rotation about the center of mass, then there is one more extra simplification, which is this one here. So let's talk about work now. So we know how to write the kinetic energy. So now work. Remember, work is force times displacement, right? So the dot product. And so what are the forces that typically do work? Well, we're going to consider weights, and we're going to consider spring forces do work, and we know how to write that. This is mg dot h, right? And this is 1/2 kx squared. So we've seen that before. There are forces that are going to show up a lot that they don't do any work. For instance, here the normal forces don't do work. Friction force, if you have a rolling without slipping, this friction force is not going to do work because this point is not moving relative to the ground. And any force where there is no displacement along the direction of the force, that force doesn't do any work. Another important point to consider is when we have couples that are causing rotation, so then the work done by that couple is m times the change in angle. If the couple is constant, this becomes the work done, and this is only true for rotation. And now we come to our favorite principle of work and energy, which is a Balance law. It says that the kinetic energy you start with plus whatever you put in and out, the work you do, is equal to what you end up with, the kinetic energy that you end up with. And here you have to include both translation and rotational kinetic energy. Now let's look at one example to see how this works. So we have this wheel that is 50 kg and there is a force of 50 newtons applied to the wheel. You're given the radius of gyration right here, and you're asked to calculate the angular velocity of the wheel after it has rotated 10 revolutions. So let's see how to do that. So let's start by drawing a free body diagram. So we have the weight, the pushing force, we have the friction, and the normal force. So this is rolling without slipping, so we can safely say that the friction is not going to do any work because this point is not moving relative to the ground. The normal force doesn't do work because there's no motion in the y-axis. Also, the y component of the push doesn't do any work. So now we can write the work done. The only force that is doing work here is you have the work done by the push, the x component of the push, and that is 50 cosine of 30, right? And then so you have to count the distance that it traveled and convert that to revolutions. So this would be 10 revolutions pi times and then 2r, right? 2 pi r. So that gives you 1088 Newton meters. So because this thing is rolling without slipping, we can safely use this kinematic relation here. And now we can write our kinetic energy, right? So we can write, remember this is what we want to write, the kinetic energy that I start with plus the work done is equal to the kinetic energy that I end up with. So I start with 0, have no kinetic energy. I'm going to end up with this much kinetic energy here, right? Which is rotation plus translation plus rotation. And so then I can rewrite this and do the simplification here. And O here is just the center of mass in this case, right? So we have kinetic energy of translation, kinetic energy of rotation. I use this expression here, and I get this here, and this is my final kinetic energy. I could have done this as also the kinetic energy about that point, and you're gonna get the same answer. So now let's look at putting everything together. We have work. So initial kinetic energy plus work done is equal to final kinetic energy, and we can solve for omega and find the angular velocity. So let's look at one more problem here. This is a problem where we have pure rotation. So we have this pendulum here. It's going to rotate this way, and you want to find the angular velocity when this thing is 90 degrees, when the angle is 90 degrees. So, and again, so this all comes down to writing the forces and the work done and the kinetic energy initial and final. So first, these reactions, they don't do any work because, well, there's no translation of that point. So let's calculate the work. So this thing goes from here all the way down there. That's the delta y, right? So delta y goes this much. So then the work done is mg times the amount that it goes down, right? So that is 90 degrees, and 1.25 is the radius. So that's the work done. The work done is 6,013 newtons meter. So now we calculate the moment of inertia about A, about this point, right? So we're given the radius of gyration, so calculating the moment of inertia is easy. And now we can write the initial kinetic energy and the final kinetic energy. The final kinetic energy is translation plus rotation, but in this case you just need to write the rotational kinetic energy because this is a pure rotation about A, and that gives you this. So now we are ready to write our balance equation. Initial kinetic energy plus work done is equal to final kinetic energy. Put in the numbers and solve for omega. Okay, so this is all there is to this quick chapter on energy. And so let me know if you have any questions.